having troubles telling how I feel, but I can dance.
Hello and welcome to the video on vector valued functions. So, the first thing I'm going to mention is that we've learned about parameterizations, right? Parameterized curves. So, for example, c of t is equal to x of t, comma y of t, and even z of t if we're working in 3 dimensions, right, in space. Okay, so this is what we've learned so far, how to parameterize a curve. So this is a parameterization. I'll just abbreviate here. So that is a parameterization of a curve. But now what we're going to do is make it, or not make it, but kind of turn it into a vector valued function. So this is what c of t is. C of t, for example, in 3 dimensions. Here's our x, y, and z. Let's say c of t looks like this. It's kind of just floating out there in space, okay? So that's c of t. But now what we want to do is kind of just attach a vector to every point that we see. So based at the origin, so we're going to base that at the origin, draw an arrow straight up, and that makes a vector to this point. And we'll do the same thing for this one, and the same thing for, let's say, this one. Okay, so we're basically drawing a vector to each point on this curve, which now makes it a vector valued function, so not c of t anymore, but we're going to call it r arrow of t. Okay, so r arrow of t is going to be a vector valued function just because we attached a vector representation for each point. Okay, so r of t, it's going to look the same exact thing that you see on c of t, but now instead of round brackets, we're going to have arrow brackets. So we still have our same x of t, y of t, and z of t, because we want to get to the same point, right? So this is a vector valued function. So I'll write that here, vector valued. So this is, so vector valued function, or we could also call it a vector parameterization. Okay, so like I said, all we did was attach a vector to each point on our curve based at the origin. And just another thing, t is still our parameter, right? So parameter, and again, it usually represents time. And then x of t, y of t, and z of t are our components, or coordinate functions, they're called, okay? So I'll just call them components here. Components, or you can think of them again as parametric equations. Okay, so now I'm going to explain the difference between a curve versus a path. So this is more or less like a technical differentiation, and not differentiation as in like we're going to derive something, but just a distinction here. So what a curve is a set of all points. So curve equals set of all points. Okay, so that would be more or less like our x of t, y of t, and z of t. Okay, so all of these that are hit, or I usually use the term hit, that you can reach or achieve as t, our parameter variable, ranges over the domain of r of t, r arrow of t. Okay, so, and on the other hand, a path is instead a particular way of traversing this curve. So way of traversing or moving. So traversing or moving on the curve. And I'll draw a couple examples here to show you what the difference is. So let's say I'll draw like little examples down here. So we have a circle, okay? And this is curve C, all right? So this is the same curve, right? Let's say it's the unit circle, okay? So it crosses at 1, 1, negative 1, negative 1. Okay, this is the x and y axes. These are the x and y axes. So this is our curve. It's just sitting there, right? But let's say our one of our r of t's, it starts at theta equals 0. So we're at this point right here, okay? And then we, as theta increases, we go around the circle this way, okay? And then let's say theta is going from 0 to 2 pi, so it'll just go around once and stop, okay, in the counterclockwise direction. Now, let's say we have the unit circle again. Okay, so here's our same curve, right? Curve C. And again, this crosses at 1, 1, negative 1, negative 1. So this is the same exact curve that you see on the left. But now, this time, we're starting from theta equals 0, and we're going to negative 2 pi. So then that would go this way around the circle, right? Once around the circle in the clockwise direction. So that would be a different path, but along the same curve, right? Okay, and I'll do one final example. We'll do that over here. Same curve, okay? So we're on the unit circle. So this is 1, 1, negative 1, negative 1. Okay, and so this is curve C. But instead, now let's say that theta goes from 0 to 4 pi. So what that means is we're going to start here at 0, and it's going to go around. Okay, so we're going to go around, reach 2 pi, so we're going to come back here, but we're going to keep going. So we're going to go around. So this last example demonstrates how you can even, due to a certain path, it might even repeat over itself, like trace the same curve twice, 3 times, or even more. Okay? So that's pretty much it for curve versus path. Now we'll move on to projecting onto planes. So projecting onto planes. Okay, and here again we don't mean airplanes. We just mean two-dimensional flat surfaces. Okay, so let's say we have a certain r of t, r arrow of t, and that is given by cosine t, sine t, and t as our z component. Okay, so this actually looks like somewhat of a spiral. So I'll draw a quick sketch here. Here's our x, y, and z axes. And this actually looks like something like this. Okay, it's going to go around and continue on upward. Okay, so something like that. And what we're going to do is project it onto the each plane. Okay, so first we're going to do projection onto xy plane. Okay, and to do so, what we have to do is basically just make the other component, the one that you do not see here, so the z, for example, we're going to make z component equal 0. Okay, so our new projection, I'm going to call it p arrow of t, is going to equal cosine t. We're going to keep that x component there. Sine t, we're going to keep the y component, but we're going to make the z be a big 0. Okay, so what that does is basically flatten this graph, the one that you see here on the left, down onto the xy plane. It's going to flatten it, like squish the z component to 0. Okay, so what we're going to have on the xy plane, I'll just draw a little sketch here. So let's say this is our xy plane. Okay, so here's our x and here's our y. What that would give us is actually just a circle, right? Because if you see the graph here, all we have is cosine t, sine t. So this is actually just the unit circle, right? So that's what we have on the xy plane. That's our projection there. That's what we would get if we shine a flashlight straight down on this graph. That's what would appear on the xy plane. Okay, so now let's do the same thing, but now we'll project it onto the yz plane. So projection onto yz plane. Okay, and to do this, that means we have to set our x component to 0. Okay, so x component goes to 0. We want to squish the x, everything going in the x direction. So that means on the yz plane, so this would be the one up against the back wall here, if we were looking at a room. Okay, so this is our yz, so this is y and z. And if we do that, our projection would look like the following. So we'd have q of t is equal to, and we're going to make our x be 0, and then we're going to keep the other two, right? So sine t, and then a t. All right, so what we're going to get is actually something that looks like a sine graph, but it's just going in a specific direction here. So something that looks like that. Okay, so that's our projection there, and then it'll keep going into the sine graph as it goes up and up. Alright, and then the last one, I'll just squish it down here, is our projection onto the xz plane. So onto, here I'll draw a line, okay? So projection onto xz plane. So that means that we want our y component to be 0. So y component is set to 0, and our projection, the vector parameterization for the projection, is going to look like cosine t. And then for y, we're going to set that to 0, and the last component is a t. Okay, so on the xz plane, our sidewall over here, let's see what that's going to look like. So we have our x-axis and our z-axis going straight up and down there. Okay, and what we're going to get is actually a cosine graph. Okay, and it's going to look like somewhat like this. Okay, so something like that, and it'll keep on repeating as we go up and up. All right, so that's how we do projections. Basically, whatever plane you're flattening it onto, if it has 2 letters, and you're starting with a 3-dimensional graph, you're going to identify that 3rd letter that isn't there. You're going to make that component, whatever shows up for that component, equals 0. Okay, and that's how you get your formula or your parameterization for your projection.
I was a dancer all alone. Dance, dance, dance.